Welcome to day 2, late afternoon talks here at Recon. I'm here today to talk to you about reverse engineering Patch Tuesday. Patch diffing is something I do quite often, and you'll see how into it I am hopefully during the talk here. My name is John McIntosh, and I'm here from ClearStack Labs, which happens to be my company. So again, real quick, who am I? You'll find me on social media at Clear Blue Jar. I'm a security researcher, founder of this small company, just me, at ClearStack Labs. I'm an open source dev, so you'll find some of my tools out there that might help you with your vulnerability research on GitHub. And I'm a blogger often, a speaker sometimes, and once in a while I do some training here and around areas. But today we're here to talk about Patch Tuesday. And I assume everyone's familiar with Patch Tuesday. Happens, a bunch of CVEs are released from Microsoft. From the Microsoft Security Response Center, they are dealing with all the submissions from the bug bounty researchers they're working with, and they're dealing with quite a few submissions each time. And they investigate the reports that come in, and they decide which ones they want to fix, which ones are critical, and they basically triage all the things that are coming in. There's an article that was talking about 20 years of security with Microsoft, and in there's some facts. They've done almost 8,000 CVEs over the past 20 years, triaged around 70,000 cases, and they collaborate again with these security researchers to fix the bugs. And that's a good thing. And you'll see those reports coming out here in a big list that they publish in this security update guide. Now, this security update guide is going to be important for us because we want to know everything that they fixed, what's inside of that fix. You can see the lists. You can't read this list, but every month they'll publish about 70 CVEs, and they'll give you some kind of metadata, some background information about those CVEs, and maybe where they might be found. Since last May, there's been 186 more, and every month you'll just have a new, fresh set of CVEs to go and look at, explore, and investigate. Each CVE, if you were to click on that, it gives you some information, some context or background. And this one says Windows Lib Archive, so it might give you a hint as to where that might be. And they give you some more information like how critical it is, the CVSS score, the impact, if it's an RCE or privilege escalation, just some more context for the CVE. They might tell you if it's a local attack vector or otherwise. And they even have this section, an FAQ section, where they give you some more hints as to, what was the vulnerability and how it might affect you. In this case, it's an authenticated attacker with guest privileges and something to do with a RAR file. And that's actually more forward-leaning than most vendors that you see out there. They're not giving you that level of detail or information. But I'm still going to say, I want to know the answer to this question. What actually was fixed? Which binaries were updated in that big list of CVEs that came out? And then sometimes though, it is clear. Like you can see this example here. This is telling you the exact file where the issue is. It's http.sys, and that's very clear. But when you don't have that level of granularity, sometimes you don't know where the actual fix was taking place. They'll give you the general area, but you don't know what was affected. So I want to know. If what was fixed was critical. Is it likely? Like, am I at risk? Is my infrastructure or company at risk from this new vulnerability? And the details are unclear from just the CVE report, but we can do better. But we basically start with this picture. We have this blurry picture of what Patch Tuesday looks like without any information. We don't know what's going on. We can get some more detail by relying on the security community. You guys out there doing the blog posts, doing the GitHub POCs. ZDI does publish some more information about patch reports every month. And so these blog posts are helpful. As you walk through, you're like, oh, this is actually what they're fixing. This is how you would either take advantage of this or mitigate this. So this is a nice blog post. I sometimes post some Patch Tuesday diffing items out there. And sometimes you get these nice POCs as well that give you really more detailed information on how your services or products might be vulnerable. So as you progress, this is the report from ZDI, and they'll just give you a big list and give you maybe some more highlight what was important, what wasn't, what's exploited in the wild. And so your picture starts to get a little bit less fuzzy and a little bit more clear as you look at these external resources. But what if we wanted to not rely on those resources and go see for ourselves and define something I like to call binary truth? And this is something that you can do by leveraging patch diffing to move forward with this. And so our picture, what I'm hoping to provide is like this really clear picture. This is exactly what has changed. This is the fix that they have made. And that's not always possible, but at a high level, it is possible, and I'll hope to show you guys that today. So again, we're going to take you from this blurry picture, from the big CV list, to this real clear picture of the actual things that have changed. And we're going to reverse engineer Patch Tuesday. So that's the intro going on, and here's one of the topics that we're going to cover. We're going to get into the power of patch diffing. We're going to talk about a very old patch diff from MS Blasterworm. We're going to reverse engineer Patch Tuesday. I'm going to talk about something called binographies, and I'll explain that here shortly. So Patch Tuesday, let's start with that. So again, Patch Tuesday happens once a month, and it's when Microsoft and other companies release software patches on a regular basis. That regular basis is important. It happens every Tuesday, or second Tuesday of every month at 10 a.m. Some people are really excited about this, and they built a countdown timer, and then you're sitting there like, okay, 2 more days, almost time for Patch Tuesday, and I kind of get excited about that because I do a lot of research in this area. But to each his own. So why Tuesday? This is from the article talking about why they or the history, and they say they give you Monday to kind of deal with any issues if you're in IT, and they give you the rest of the week to kind of deal with any issues that come up as a result of doing the patches, and mostly to avoid what happened last summer when CrowdStrike had an issue that affected airlines kind of across the country. And also, you don't want to deploy on Fridays. It's the basic lesson learned there. So Microsoft patches, they can apply. They're not only security issues. They can also bring in new features. So you might see that in your diff. Just something to keep to be aware of. But if you're trying to research this, they give you the CVE list, but they also give you these knowledge base update articles. And from here, you can get a clear list of all the builds that Windows produces, and get some more information like a file manifest for each update. And sometimes they have these out-of-bound updates. This is more background of what they're producing for some of the updates coming out. But I do want to talk about the history a little bit. For the past, I think, 23 years, they've been doing regular updates. And then it was Patch Tuesday itself was actually introduced in October of 2003. And there were several reasons for that. And back in the early 2000s, there was not really a regular cadence of patches. They were kind of more ad hoc. The Blasterworm came out in 2003 and affected a lot of machines, and that was another impetus for bringing updates on a regular basis. And then Bill Gates in 2002 introduced the TCI, which I'll explain here. Again, they had these, they would ship updates in the early 2000s when they were ready. Not on Tuesday, on the second Tuesday of every month. It was like, oh, this is done now, let's push it out. And so you can imagine maybe people are not ready to deploy those, and it was just not more of a formal thing. The Blasterworm, if you look on Wikipedia, you can see this hex dump from a long time ago from this virus. There was a message in there. It says, Billy Gates, why do you make this possible? Stop making money and fix your software. This was a worm that had big impact and was a wake-up call for Microsoft. That message there was probably more funny now than back then because of the impact. But we'll dive into Blasterworm here a little bit later. This was from the Blasterworm. I'm not sure if any of you were in IT at this time. I was in university my first year, and I saw this message quite a bit. I was working IT, and we would try to fix all these machines. And if we didn't remove the machine from the network after we re-imaged it to fix it in the first place, immediately we would be hit again by the Blasterworm. I would see this RPC server crash over and over. So this was a very familiar thing to me back from 2003. Again, that had a big impact, over 1 million computers, from this article at this time. And then the last thing was this TCI, where Bill Gates was trying to say that our computers are very important. They need to be as reliable as your utilities, like running water and all those things. So you can judge for yourself to see how they're doing, but software is complex, and to make that stable, it's a big deal. All right. Now I'm going to show you the evolution of how kind of updates worked. Back, you can see security bulletins, which was the old way they were publishing updates before the new catalog. And you can go back in time all the way to 2004, And you can kind of see like almost like blog post updates. Here's your bulletin, some information about that. But before it was more like a suggestion. Microsoft is distributing this bulletin to increase awareness. You should probably do this. And this has evolved over time. They went from there to service packs. And the service pack was more like a big collection of all the updates they would distribute to you on a CD-ROM for those who were around for that time. This is me. And now we got Windows Update. And for the first 10 years, Windows Update was just really a web app on Internet Explorer. Vista had the Windows Update agent, and then Windows 10 and 11 and have now made updates mandatory, and probably for the better. So modern day MSRC, they have a bug bounty program working with researchers, and they publish now this MSRC security guide. And we're going to focus more on that now. So the security guide provides CV details, and they provide useful FAQs, and they even now provide something called CWE information. So this is an article from 2024, and they were just describing how they're adopting this policy to be more forward-leaning with the information. And the CWE is really powerful because it tells you what type of vulnerability was fixed. And so, for example, in this Windows perception service, wherever that is, the weakness is a time of check, time of use, race condition. And that will give you some context and some ideas when you're reverse engineering of what to go and look for, or what to go and reverse engineer in the first place. So that's really powerful too. And again, kudos to Microsoft for publishing that and providing that information. But I'm still saying that the mystery remains. I want to know what was actually fixed, which binaries were updated, and is this thing actually critical? So how do we do that? We step into the power of patch diffing. And so, patch diffing is just a technique to help you scope your reverse engineering and kind of focus you in that buggy area of code. It's built on just two basic superpowers. One is just the power of diffing. That's really ignoring everything that has changed. I'm sorry, ignoring everything that stayed the same and just focusing on reversing that. Focus on the changes, things that stand out and that are different. Too much coffee today. Sorry, guys. And ignoring all the similarities, all the things that have stayed the same, because all you're looking to see is they fixed the security issue. Let me just focus on that area. And it becomes, again, like a map or a compass to this buggy area of code. So with the diffing, you combine the power of reverse engineering. And there, we're just trying to observe, infer, and understand what has happened. And we can use modern-day tools to help us do that. And they're really powerful in showing us the path there. So in the end, we're seeking this binary truth, what has changed, and to complete our understanding using the two superpowers. And now we'll try to prove it here. So this is CVE 2024 2698. And it's a Windows kernel privilege escalation. And it says down there it's an integer overflow. So again, we have a lot of context. When it's actually the Windows kernel, it means the Windows kernel. And you have to diff the two 11 meg binaries. There's about 30,000 functions across the two binaries. And with diffing, actually, you can get that list on average down to about 50. And sometimes, actually, you can get that list down to just one or two functions. So if we take a look at this diff here, this is an output from my tool, gdiff, doing a diff of the full Windows kernel. And if you look at the list, this is a table of contents showing there were no functions that were deleted, there were no functions that were added, and there were only two functions that were modified. So out of the 30,000 functions, that's a pretty narrow window to go look at, and you have a microscope to go and see what the security issue was. So from the diff, we identify what has been changed, focus on that, and now we try to reverse engineer this. Now, it may be hard to see from where you are, but the first thing there that was changed is that there was a realloc function, and then they've added some other feature flags and some RTL ulong multiply, and we'll look into that. So from the call diff, we can say that 3 new functions were added to this. And we start to see kind of maybe we'll figure out what these ulong adds are. Again, if we look at the old function, what has changed is the parameters that are passed in have changed. And it looks like here, if you can see from this, is they've added several functions that are trying to do safe integer calculations that are now going to be input into this realloc function that's still there, but they're just protecting the parameters going in. So you know that they're trying to prevent an integer overflow with these safer functions. And so, and the giant 30,000, the giant kernel that we just saw down to one function, down to this, you can say, oh, I know what has changed. I understand. I can root cause probably what that privilege escalation was. So we can also, with reverse engineering, answer the question of how can we reach this function? So kind of with simple call graph analysis, we can kind of find the entry points and maybe find a path of how would this even be taken advantage of, or what would I need to mitigate potentially to lead me down to this modified function where it came from, or the code path you need to find. So yeah, basically through RE, we began to understand root cause, how this might be triggered, and how it might be dangerous for us. If we look at another example, we have CVE 2024-3863, and this was a TCP/IP issue, and TCP/IP.sys, and it had a very high CVS score of 9.8. And immediately I want to know what is fixed, is it critical, and I have this fourth bullet here called CVE hype. A lot of people out there, when something like this comes out with a high CVS score, they'll start to post what I call CVE hype. And it's basically, they know it's in the network stack, and they know it has a high CVSS, so they start to say things like, oh, this is wormable. You guys got to watch out, got to be careful. This thing's going to hit hard. And you don't really know the answer to that question, maybe until you go look for yourself. And so people love to post CVE hype. Sometimes I post CVE hype. But I was posting binary truth is what I like to say. So I was just showing you the diff. I was just showing you what had changed. And you could go, and this is the output from the tool. And from this diff, I could go and see that, oh, the security-related function here was this IPv6 process options. If we want to go look at that a little bit closer, I could say that they removed a method and they added a different one in. Now, from this context, you don't know what the issue is or what the problem is, but you can actually go and have a starting point. So through the patch diffing, we know the area that was effective in IPv6. And then you have that context to go and then start debugging and try to figure that out a little bit more. So that's the power of patch diffing. Is this new? And we know the answer to that is no. But I do want to tell you a quick story about the origins of Patch Tuesday and how MS Blaster Worm kind of fits in there, because I did some research on this, and it's pretty interesting how this goes. So back in 2003, there was MS Blaster Worm that came out. And right here, according to the court papers, the original Blaster was created by a hacking collective called Xfocus. And how they created it is they reverse engineered the original patch. So they patch diff the patch to figure this out. So this has been going on at least since 2003, and I'm assuming before. But it's very interesting what happened as a result. So here's a quick timeline. 2003, August 11, Microsoft began investigating a worm that was going around. It was known as the Blaster Worm, and it was resulting from this vulnerability here, the Microsoft Security Bulletin MS-03, which I have a copy of right here. And this is before the days they had automated patches, and they had everything coming into play. And this was a buffer overrun, which today we're pretty heavily mitigated against. We have a lot of exploit mitigations that would stop you from just using a Stack Overflow remotely with ASLR and all those things. But this is in the days that those things didn't exist. And so this is RPC exposed on the internet before firewalls were prolific everywhere too. And so you can imagine how that could have a really big impact. So the bug was actually discovered by this group called the Last Stage of Delirium. And they researched it. They realized this was a serious issue, and they provided Microsoft, or they reported to Microsoft the result. They developed proof of concept codes, so POCCs, not POCs like we have today. But the language was a little bit different, but the same thing was happening back then. They had a paper and a download. I'm pretty sure they must have presented it, the Recon equivalent of that time, or maybe not. So due to this big impact, again, they disclosed to Microsoft and not publicly. This might be known as an early coordinated vulnerability disclosure. And then 9 days later, after that patch diff, the Xfocus group actually published the full bug in a nice blog post here. And so all the details were there, and this is a copy of that. You still can find it on the archive.org. And basically just detailing the what had happened or the bug itself. And I'll show you that here in a second as we look. But this might be known as a uncoordinated vulnerability disclosure, or we do this a lot now today, but again, they didn't have the patch infrastructure and update infrastructure that we had. So this was after the patch, but still, I think this would be uncoordinated. So 17 days later after that, MS Blaster original version appears and is detected by Microsoft. And it affected over, again, we've got now 10 million machines from this quote. I'm not sure how big the impact was. I was pretty young at the time. But then we have about 8,000 days later, and we have, that's like modern day right now, we have a security researcher diffs the original Blaster RPC-COM vulnerability. Because I wanted to know how did they do it. And I'm also curious, what tools were they using? And what does patch diffing 20 years ago look like? I don't know the answer to that, but we'll see what it looks like today. So 20-year-old patch diff, let's go with that. So here are the requirements. To patch diff, you need the vulnerable version, the fixed version, and then some type of tooling to help you see the binary more clearly. So how do we get 20-year-old binaries? Well, we go find the very, very old base edition of XP, and we go ahead and install that in a VM. Now, we also needed the patch, and that was linked off that security bulletin. And this is the Wayback Machine, and it had this link here. I'm like, great, I'm on the way. Click on this download link here, and then it didn't have a copy of that. But some random FTP somewhere always has what you need. So go grab that, and I took it off of there and ran it in my VM. I felt comfortable running it in the VM, and I was happy again. And all of a sudden, I could answer the question, which binaries are updated. Not in the same way I'm going to answer them in modern day, but from here, I just did a hex dump of the actual update itself, and you could see several RPC vulnerabilities listed in there. And to really see what binaries were changed, I installed the update on Windows XP, and then I noticed in this reg key, it's called pending file name operations, and it's a way for you to change system files because you can't move them when the system is on. You're unable to. This is a method for doing that. You can see the list of binaries that were going to be updated on the restart. So after the restart, I grabbed those binaries, and I already had copies of the old binaries, and I finally had my list from the 20-year-old patch diff to go and investigate to see what they saw 20 years ago for the worm. So I threw this into Ghidra. I did some user native tool version tracking, and I was able to identify the function you can't see from there, but it's called get path for server. And this is actually from their original Xfocus report, where they were pointing out that the stack size was only 20 hex bytes, and that I found that in modern day, I matched that up here with Ghidra. You could see that. And again, this was a buffer overflow. It progresses through over RPC, so that's a way that like over the network. And then the basic buffer overflow issue is that they reserved 32 bytes for a 16-bit, or sorry, a 16 Unicode character machine name, but the path there could take could take file names that were 256 Unicode characters. So they had 512 bytes going into 32 bytes standard buffer overflow, and enough to take advantage of the vulnerability. You can see the diff here, and you can see the change there. They fixed it by putting it back down to back to 512 bytes, or 256 Unicode, and that was the same diff that they saw 20 years ago that enabled them to build MS Blaster. These are just some more references of the original report, matching it up with Ghidra. And then they probably didn't have the pseudo-C decompilation that makes it even easier to see that this is a string copy happening. But they had enough information. So the main point of the whole looking at MS Blasterworm is that a patch diff of the RPC vulnerability led to Blasterworm, and that MS Blasterworm was really the primary catalyst for Patch Tuesday, or one of the three primary catalysts. And so you have this patch diff being the parent of Blasterworm, being the reason for Patch Tuesday, and probably the reason why I'm standing here talking to you today about Patch Tuesday. But very interesting looking at the history and thinking that Patch Tuesday was born of a patch diff. So which brings us back finally to our topic of reverse engineering modern day Patch Tuesday. And let's leverage patch diffing and figure this out. So we want this clear picture, and we're stuck with this blurry one. What CV was updated, what is binary truth, and I'm going to share with you my technique for going about and doing this. So manually, you would need to get these first 4 steps. You would need to determine the binary for the CVE, which is a hard problem because there's no direct mapping from CVE to binary. Download the binaries, diff them, analyze, reverse. So let's look at how do we automate the first 4 steps. And I'll talk really quickly about my path to get there. It was basically a series of experiments that were all reverse engineering related that kind of led me down this path. So my first thing was I was jumping into research. I wanted to study vulnerabilities, and if you're also entering into the space of vulnerability research, I would suggest this path. because really it lets you look at, what is the bar for modern CVEs, what do bugs look like, and it's a nice way to get into the space and have a nice scoped RE problem. Every Patch Tuesday, a new problem for you to solve. So I was doing this myself to figure this field out. In doing so, I did write a tutorial on how to do that. The main idea behind this was using CVEs as North Stars to point towards buggy code. And this is a public thing out there, and it's just a tutorial on how to do patch diffing with Ghidra, and that was from a couple years ago. So those two things, I learned a lot in that process. And then I started also building a lot of tooling. I like to write tools and open source them. One was called CVE Markdown Charts. And it's basically me doing a bunch of web scraping and bringing this all into a script that would print out nice charts that look like this. And I would start to analyze the patches, start to get an idea of what type of vulnerabilities were out there, like what was popular. And from this context and from doing a lot of this diffing, I'm setting me down the path for this automation. And so, yeah, just some things here from my blog posts. There was my progression, and there's also this resource out there. M417Z, I actually don't know his real name. I've met him on Twitter, or X, as the young people call it. But WinBindex itself is a major resource. This is a resource that catalogs all the Microsoft Windows binaries over time, and it gives you a direct download link to download those binaries directly from Microsoft. And Microsoft is hosting those binaries to allow you to debug things properly. But this resource right here allows you to look up any file. And so imagine using that with your automation, or with patch diffing and automation. So I studied WinBindex itself. I did a short talk on a experiment that I did with WinBindex, trying to brute force download links instead of having to figure some things out myself. That's an old talk you can go check out. I wrote a tool called Ghidra, and this is really the enabler for me to do command line patch diffing and do this at scale. And so if I can do this at scale and I have all these resources, this starts coming together, and I can start doing automated patch diffing. And that's kind of what we're talking about doing here together today. So I created a tool called WinBindiff, and it's basically combining Ghidra with WinBindex. And a similar thing here where you're defining the file name, and you can start to write the story of a binary over time. I presented this at Black Hat last summer, not this year. It's not happened yet. And so these are some of the slides from this. I was basically telling the story of, what if I wanted to see changes over time? What if I wanted to tell the story of a binary, the biography of a binary, or the binary biography? And then I'm not sure if this is marketing or whichever, but it's a binography. This is what I want to be able to create, the story of a binary over time. And if I can do that for a binary, I should be able to do that for Patch Tuesday as well. So this is a quick output, and I'll show you a better output here. But the end result is going to be this table that has a CVE, and you can't see it from where you are, but all the changes, all summarized kind of on a single page. Again, if I could automate diffing between two binaries when I'll Patch Tuesday. So to reverse engineer Patch Tuesday, we're going to do Ghidra, which is my command line diffing tool, plus the database of Windows binary files, and my magical CVE matching algorithm, which I'll explain here next. So here's the algorithm. First, you need to pretend to be a data scientist, and then you have to get out your Jupyter notebooks, and then you just start making things up. And you start doing some web scraping. So you pull this information together, you pull that into a big Python notebook, and you start trying to answer questions. The big picture is this, though, is that every Patch Tuesday, hundreds of binaries are updated, and the only ones you have to consider are the ones that actually have been patched. So the build number has increased. And then you glean the details, and you don't try to be perfect. You just have to be good enough. You want to go from 1,000 binaries that could be down to 100, down to maybe 3 or 4 per CVE. And it gives you really good insight on what has changed and what actually is related for this problem. So my information sources, one is the biggest one is the MSRC catalog with all of its information and CVE data that's there. You throw that into Jupyter notebooks and some pandas data frames, and you can start building things like this. I know that for this update, this KB update, with this build number, this many files were updated. And so that takes me from 1,000 down to 50, or in this case, actually 173. So it's not quite good enough yet. Then I start doing some correlations, and we use things like the binary name or some maybe binary description, and you kind of correlate those things together, and you build these tables. I'm not going to get into details of all of those things, but you can start asking questions even from the data that you have. You can say, for these CVEs, which ones are a bit too noisy? I mean, the matching is too broad. Well, some of the names are not very descriptive. Some of the names for CVEs have like Microsoft Windows, and that's about it, and you're going to match too heavily on there. So you can try to improve those things, but as I look through this over time, I was able to map CVEs to binaries and then improve that process and basically build a list for every CVE of which binaries potentially could match. And then from there, you diff each of the ones, and then you can kind of you still have to do some reverse engineering, some understanding, but it brings you down from 1,000 to 100 to maybe 3 or 4. So how effective am I at mapping binaries to CVEs? Well, this is a chart from I think 2016. This is not quite modern, but it's an older chart printout. And the blue is where I have mapping for CVEs. And so it's I don't know, it hovers around 60 or 70%. Sometimes it's more, sometimes it's less. But I've got coverage here, and so every Patch Tuesday, I should be able to do to build you this binary binography of all the changes. So again, a binary binography is telling the story of a single binary, and the Patch Tuesday binography will be telling the story of the CVEs over Patch Tuesday. So I do have a video. I don't know the sound. It's not very exciting. It's a command line tool, but I'll try it anyway. I'll try to explain it. Yeah, I didn't hook up the sound, but that's okay. We don't need the sound. So this is basically me running, hey, go get June's updates. It's going to go through and hit that WinBindex server and try to download every single binary that's related. It's pulling those down locally. And let's see if I'm going to skip a little further, or can do this manually. Oh, still going. Again, not very exciting, but I'll show you the end result, and hopefully the end result is more exciting. So after it's doing all the binary download updates, it's throwing all of these into Ghidra, analyzing the binaries in parallel, and Ghidra is going to run and output all of the, you saw some samples already, but all of the markdown. And in the end, you get this giant CV list, and you click on a binography, and that's all marked down. It's also JSON as well, but then you have this big table, and for each CVE, you have a list of binaries, and you can click on the functions themselves, and it should take you right to the changes that have been made. And so this is the workflow that I use to understand and reverse engineer Patch Tuesday, but that's the whole process of doing that. So automating, correlating CVEs to binaries, and then I'll show you the kind of resulting. So this is we'll look at. Oh, don't click anything too much. Take a look at June. And so GitHub doesn't allow me to do this too well, but for every CVE, you see you have Windows shortcut files, and then I try to bring that down to something that might match. And then for each one of these things, you can click on. It'll take you to the actual diff that has happened, and you start to evaluate kind of what's happening for each of the CVEs. Basically, reverse engineering Patch Tuesday is a whole bunch of diffs with some correlation and getting that understanding of what Patch Tuesday might be. So switching. All right, so that's, Patch Tuesday binographies, telling the story of Patch Tuesday, and in the end, we're going to provide that binary truth so you have that full picture of what's happening with Patch Tuesday. WinBinDiff itself, I did demo at Black Hat. I've not released that open source, but I have released Ghidra, and I've told you how to do it. But Ghidra itself is the engine that I use to drive the whole process, and that's the most powerful piece you have in there. So that's all I have for reverse engineering Patch Tuesday. Hopefully, I've shown you how to maybe go from this blurry picture, to a more clear picture, and brought you to the end here. But that's all I got for you.